Hi guys, Audrey here. In this video, we're going to talk about the test for divergence. Let's get started. All right, so we saw that the test for divergence, also known as the nth term test, tells me that a series can only converge if the associated sequence converges to zero. In other words, if we do the limit as n approaches infinity of a sub n and it does not equal to zero, our series diverges. If it does equal to zero, the test for divergence fails and we have to do something else. So let's apply the test for divergence to a couple series, talk about what the answer means, and if the test fails, we'll just state that. So the first problem we're going to do here is the sum from n equals 1 to infinity of 2n plus 1 over n plus 1. So if we're applying the test for divergence, that means the first thing we need to do is evaluate the limit of the associated sequence. So in other words, of that general term right there. So we're going to evaluate the limit as n approaches infinity of 2n plus 1 over n plus 1. Now plugging in here gives me infinity over infinity, but we can take the big stuff, we can take our dominant terms. So in this case, our dominant terms are 2n on the top and n on the bottom. So this is the limit as n goes to infinity of 2n over n, which is just 2. Okay, so what that means is this series diverges. That 2 does not equal to 0. So by the test for divergence, the series diverges. There we go. That's our answer. Now, why does that mean it diverges? So remember, a series is the sum of all of these elements. So I'm doing the sum from n equals 1 to infinity of 2n plus 1 over n plus 1. So first I'll plug in 1, and I'll get 2 plus 1, that's 3, over 2, plus then I'll plug in 2, and that's 5 over 3, plus then I'll plug in 3, that's 7 over 4, then I'll plug in 4, that's 9 over 5, and so on and so forth forever. But the fact that the sequence here converges to 2, which is what this is saying, the sequence a sub n converges to 2, tells me that in the end, when I get really, really, really big, it's like I'm adding something that's so close to 2, it's practically 2, over and over and over again forever. So this is eventually like plus approximately 2, plus approximately 2, plus approximately 2, plus approximately 2, and so on and so forth forever. And if I add 2 to itself over and over again forever, I'm clearly going to end up at infinity. All right, so it took a little second for those 2's to catch up there. But so exactly, so I'm adding these 2's over and over and over again, and of course I'm getting to infinity. So we said the only number that I can add to itself over and over and over again and not get infinity is 0. So let's look at this series, the sum from n equals 1 to infinity of 1 over 2n plus 1. So now I'm going to evaluate the limit as n approaches infinity of 1 over 2n plus 1. Well, that just gives me 1 over infinity, which is 0. So what that tells me is that the test for divergence fails. So why does it mean that it fails in this case? So let's think about it in terms of what we just said. So I have that 1 over 2n plus 1. So this is a sum, an infinite sum. So it's like I'm doing 1 over 2 times 1 plus 1. So that's 1 over 3, plus 1 over 2 times 2 plus 1. That's 1 over 5, 1 over 7, 1 over 9, plus dot, dot, dot. Okay, so the values when I'm adding up here are giving me an actual number. I'm getting some number. So eventually, when we get towards infinity, when we get really, 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 really big, it's like I'm eventually adding plus approximately 0, plus approximately 0, plus approximately 0, over and over and over again forever. So there are two questions here. One, before we were adding 0 forever and ever and ever, did we manage to already become infinite? In which case, adding 0 is not going to change the fact that that's infinite. Or if we're adding approximately 0, how far away from 0 are we actually? How long is it taking us to get close to that 0? Are these significant enough that we're still getting bigger and bigger and bigger and becoming infinite? I don't know. I can't know by looking at this. All I know is there's some value in the beginning, and maybe that value is infinite. So I can't know this. The test for divergence fails. So the sequence goes to 0. So that's what this is saying. Again, the sequence converges to 0. The sequence A sub n converges to 0. The test for divergence fails. The sequence does not converge to 0. Like in the previous case, it converges to 2. Well, the test for divergence tells me it diverges. Okay, let's just look at a couple more using all of the knowledge that we learned when we were doing sequences. So let's say that I have this sum from n equals 1 to infinity of cosine of n. So the limit as n approaches infinity of cosine n, what do you guys think? If you're saying does not exist, you are right. This does not exist. Now remember what cosine is doing. So cosine kind of looks like this. If it's a function, this is what's happening. Now, because it's a sequence, I'm only looking at the values at whole numbers. So it's kind of like I have something at 1, I have something at 2, I have something at 3, I have something at 4. I don't know what those. Anyway, so like we're having little dots. I have these dots only at whole numbers. And notice those dots, they're going up, and then they're going down, and then they're going up, and then they're going down, and they're never actually going anywhere. So this is the bouncing back and forth problem, the oscillating problem. So I'm going to be adding a number, and then I'm going to be subtracting a number, and then I'm going to subtract another number, and then I'm going to add a number, and I'm never actually going anywhere in this series or in the sequence. So in this case, we say the sequence diverges. But if the sequence diverges, it for sure does not converge to 0. So therefore, the series also diverges by the test for divergence. All right, let's look at another one here. So let's do the sum n equals 1 to infinity of 4 to the n minus 1 over n factorial. Okay, so again, we're looking at the limit as n approaches infinity of 4 to the n minus 1 over n factorial. In this case, I think we're just going to look at our dominant terms. We'll take that 4 to the n and that n factorial because we get infinity over infinity. But I can't do L'Hopital's rule because L'Hopital's rule doesn't exist for n factorial. So then we end up with the limit as n goes to infinity of 4 to the n over n factorial. Now we could do a squeeze theorem here, and the squeeze theorem would be pretty intense, but we can also use our growth rate chart. So from our growth rate chart, we remember that n factorial grows more quickly than 4 to the n. So what that means is this is infinity over infinity, but the division by infinity is stronger. The division by infinity is sort of winning that infinity battle, which means that this is therefore equal to 0. So here my sequence A sub n converges to 0. But what does the test for divergence therefore tell me about the series? The test for divergence fails. It doesn't actually give me information about the series. So here we'll just state that the test for divergence fails. All right, let's just do one more here to kind of really think about things in an interesting way. Actually, we'll do two more. So let's think about cosines a little bit. Let's say that I have sum n equals 1 to infinity of cosine of 1 over n. So up there we did the sum of cosine n. We said that that sequence diverges because we've got that oscillating, bouncing back and forth thing. But here, if I were to do the limit as n approaches infinity of cosine of 1 over n. Well, now what I have on the inside is a 1 over infinity. So this is cosine of 1 over infinity, but we know a constant over infinity is 0, and cosine of 0 is 1. So here my sequence, cosine of 1 over n, converges to 1. But what does that tell me about the series? That tells me that the series diverges by the test for divergence, because it's like I'm adding 1 to itself over and over and over again forever. All right. Oh, oops. So basically, we can see that with the test for divergence, we're just doing the same thing that we were doing to see if sequences converge or diverge. So then we're making a conclusion about the sequence. Does it converge to 0? Well, if so, then the test for divergence doesn't tell us anything. If not, then the test for divergence fails. So we're going to do one more thing just to kind of remind us of alternating sequences and how we deal with those things. And then we will be done. Uh-oh. Okay, so we're going to look at the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n over n squared plus 1. Now, this a sub n is equal to negative 1 and plus 1 times n over n squared plus 1 is an alternating sequence. So that makes this series an alternating series, but we'll talk about alternating series a little bit more later in depth. So this is alternating sequence. If I want to determine if an alternating sequence converges or diverges, I need to look at the limit of the positive part. And we can remember that the only, kind of like with the test for divergence, the only possible thing that an alternating sequence can converge to is 0. So here, just a reminder, if the limit as n goes to infinity of the absolute value of a sub n is equal to 0, then a sub n converges to 0. And if the limit as n goes to infinity of the absolute value of a sub n does not equal to 0, then the sequence a sub n diverges for the same reason that that cosine of n diverged, because we have the bouncing back and forth, we've got the oscillating thing going on. It's going to be going positive, negative, positive, negative, positive, negative. So let's take a look at the limit of the positive part. So we're looking at the limit as n approaches infinity of n over n squared plus 1. We take our dominant terms, we take the big stuff, n over n squared. So the n squared on the bottom is bigger, so that's just 0. So what that tells me is that therefore the sequence a sub n converges to 0. If we had gotten 1, well then the absolute value of a sub n converges to 1, but the alternating sequence would diverge. But in this case, that 0 actually tells me that the series, I don't know, maybe it converges, maybe it diverges. So the test for divergence here just fails. All right, guys. So now the next question is, so this is the test for divergence. We've seen when it diverges, when it tells us it diverges, when it tells us it fails. So a test for divergence can never tell me that something converges. Now the question is, what do we do when the test for divergence fails? What do we do when the test for divergence fails? And that we will answer in the next video.